So I'm personally like halfway between academia and industry. So half of the time I'm in industry, half of the time I'm in academia. So the talk will be like also halfway. So the general idea is that there is like some lost chapter of computer science, data synchronization. In our apps, we use like typical commodity data structures like maps, vectors, or whatever. And there is no way, there is no generic technology to sync those data structures. Like once we have two devices, we obviously immediately get the need to sync data. For some strange reason, in a computer science textbook, there is no accepted way to do it right. For some reason. Like it was discussed in the 80s, but the money went the other way, so so this story was unfolding at a very slow rate. I started participating like in 2008, so it is much better now than back then. But the general idea is like we currently can have like wall outlet with IP packets, right? And we want to have wall outlet with data structures. Like I changed some stuff here in my app, and it goes by the wire somewhere. I don't think about it. It does it in background, and it gets distributed to all the replicas. If somebody clicks something somewhere, it gets back to me. So I just connect it, and it works. This is the idea. Very well-defined problem, very generic. Everybody needs it. There is nothing. So general approach is like we use a database. My app is saving to a database. Your app is loading from a database. What if we deal with a long-running app? Like we have to poll the database, which is not good. And generally speaking, if we lose connection to the database, that's it. We are screwed because we have no local copy. Another way to look at this problem, like it is Git for data. We have the data we need, we have it like locally, we are autonomous, but we also sync in real time. That is like the vision for it. In application to database theory, like some ideas have been said like in 1984, and it was obviously a summary of discussions of the 70s. So the general idea was like in the air, but the money went the other way. Because obviously, if you bring all the data to one big central server, then you can own the server, you can make lots of money. So, I mean, the logic is rather straightforward here. Like, it is a bad technology if it makes me lose money, right? So, but if you look from the other side, like from the client side, then it is exactly the opposite. Why can't we use rsync, for example, for such thing? Why can't rsync be our libsync for such kind of general things? Obviously, it works well. It synchronizes binary blobs without understanding what's inside, so it is generic enough. But rsync only works one way. It can update replicas, right? It can update mirrors. Because if you have two files, same name, different date, different size, what should rsync do? I mean, is it like, this is probably the new version, and maybe these are like concurrent changes. It is unclear from the context. And also rsync is enabled to sync a file which has some internal structure. So obviously to understand which is first, which is second, or maybe they are concurrent, we need to track changes. Revision, that is revision control, right? Obviously, Git has history branches. It knows which version was derived from which other version, and using that metadata, it can more or less reasonably merge the changes most of the time. With the exception of obvious cases when it cannot merge them. Or it will merge them, but that will be a bit incorrect, because it has like very vague understanding of the semantics of the data. Yeah, so we cannot use Git for this purpose for this simple reason. Git has non-deterministic merge. So quite often Git has to appeal to the developer to manually resolve the merge conflict, right? And that is non-deterministic. We cannot have an application which asks the user. Actually, Google Docs was doing that. in its early days when they had concurrent edits in the same paragraph, they would show a pop-up like which version would you prefer. I don't know. If you speak, for example, of Apple, their Office program, it was even a funnier story because it was saying like which version do you want to keep, and if you click the wrong one, a week of work disappears forever. That actually happened to me. So, but they're much better these days. Then nice new technology that is about 2011, CRDTs. Conflict-free replicated data types. Let's take all those commodity data structures, which like everybody is using to build their apps, and make mergeable versions of them. We use some metadata, we annotate each piece of data like this was added by Joel like yesterday, this was added by Jane 2 days ago. So we more or less understand which piece of data came from which site and which is the recent edit, which is the old data, and so on. Algebraically, it is very, very nice and smooth and clean, and it always like merges very reasonably without conflicts and so on. I will explain the quotes. We invented, so basically, who invented the CRDT? CRDT wasn't invented, it was coined. By the time the term was invented, the technology was already in use. And the very term CRDT, I mentioned it as conflict-free replicated data types. Actually, there are also commutative replicated data types, convergent replicated data types, and many other probably C RDTs. They mean more or less the same, but they're like equivalent in some sense. So basically, it is a vast library of replicated data types of various kinds. So that was like a happy day when that INRIA team publishes the paper with a library of replicated data types, half of which they borrowed from somebody else. But finally, we have like that full library which we can use to build apps. So finally, we can solve that problem. It is not poor engineering, right? Sort of, yes. But the problem is CRDT resolves all this merge conflicts and other issues of dealing with concurrent changes to the data. It resolves it by adding metadata. So for each piece of data is annotated, who added it, when added it. And that basically can ruin everything for the simple reason we can have more metadata than data by many times. So we can only compare this technology to Cassandra. I mean, among like massively used technologies, which are like industrially massively used, the only thing we can compare it to fairly is Cassandra. Cassandra is last right piece, but it is using metadata. You understand Cassandra, right? Massive cloud database which Apple is using on farms like of 10,000 servers because like all the iPhones are pumping data into the cloud and they have to put it somewhere. So Cassandra is like very decentralized and it has the same more or less metadata problem. They're kind of cheating. They're putting, I believe, only one timestamp on a tuple. And in case of CRDT, we have to put like one logical timestamp on a cell. And a logical timestamp is ID for replica and time. So basically two integers. So if our cell is one integer, we put two integers of metadata on top. And also because like most typical piece of data in real world applications is a small integer, and our logical timestamp is typically a larger integer, and user ID is also larger integer. So in the end, it will be like 10 times more metadata than data, which sort of ruins the day. Because like it works correctly, there are no conflicts, but you need 10 times more time to pump all the data and 10 times more servers to store it. Annoying, but it's all correct. No conflicts, asynchronized is really good. So basically, this was the story like 2011, 2013, 2015. So it was like a top issue on the agenda. Then another piece of metadata is version vectors. In case I mean, we can also refer to one like massively used industrial system, DynamoDB, which has more or less that problem, but they don't have it much the problem because version vectors is a constructs. Like if you don't have any linear history, you can, like in Postgres, RocksDB, whatever, any classic database, MySQL, we can have like transaction 1, transaction 2, transaction 3, transaction 4, and so on, linear. In such a database, because we don't have central server, we don't have linear history. So we have a vector of versions. So we say like from Jane, we heard everything till version 10. And from Joe, we heard everything till version 12. And so on. And in the worst case, for each user, we have a number. So if we have million users, then our theoretical descriptor of our version is like 1 million cells, which is not good. And that was also a problem that was bothering many people. For example, some people from the Portuguese team, I think University of Braga, which one, yes, Braga, they wrote like a stack of articles on optimizing version vectors. Basically, yes, it was a problem. Why DynamoDB doesn't have that problem? Because for them, one replica is actually one server. So in case you have 10 servers, you have 10 cells in a version vector. And this will be not servers in total, but servers touching a particular piece of data. So it wasn't much of a problem for Dynamo. Like we have nice technology, it merges well, it synchronizes well. But, well, actually, me and friends made collaborative editor which was running in production in 2012 using exactly this version theme, but it wasn't an issue because for each particular document, users edit collaboratively. There are typically not many users. Even if you have 100 users, that is not a tragedy. Even if you have 1,000 users per document, which is really rare, it is not a tragedy. So this is only a problem in some cases, but when it is a problem, it is a big one. So all these metadata problems have been more or less solved by this day. Basically, the correct approach was to use, how to say it, to version data in bulk. Like you can ship in envelopes, you can ship in logistical containers. So the idea is to ship data in logistical containers. Once you version logistical containers, you need much less of metadata. But what I'm describing is like progress of this field of research for maybe like 15 years. Just like, I mean, when I describe it post factum, it is like, what a fool have I been? But it wasn't just me, it was like a team in Portugal, a team in France, and many other teams. So, the idea, we can compare this entire story to massively run LSM databases, which actually naturally version their data because they have how to say it, SST files of old data and like less old data and new data and so on. So they naturally keep old and new data separate. So if that trick is used, then that part of metadata is not a problem as well. So obvious question for people who are bored of academic struggles I have been describing. What can I actually use? Somebody, by the way, who has an idea what can I actually use for syncing my data in my app? Please raise your hand. Like you have clear idea you're using something else. 1, 2, 3, 4, 5, 6, 7. So basically, this is like a relevant audience. Good. So currently we have like the local first world which is mostly into JavaScript, mostly. Some have Rust implementations, but they're like not working that widely. So mostly from 2014, I think that local source story continues like for 10 years, and to this day, most of it is like JavaScript. Then there are solutions for syncing databases. Like we have Postgres on the server, we have SQLite on the client, and we want to synchronize it. And some of these are actually funded companies. And the thing I like to talk about is librdx. It is like my thing. So librdx is like a replicated data exchange format. That is like a JSON-ish format which synchronizes really well. So why do I want to talk about it? Because synchronizable JSON, it is like from 2014, and it is not used really much because basically what is the good thing about, again, problem is about metadata. What is good thing about JSON? JSON is easy to read, easy to edit, right? If we put our data in JSON, we can always read it, we can always edit it, we can always debug it. We open console in the browser, we see JSON, we understand what's going on, right? So if you add that CRDT metadata to JSON, it becomes like really complicated, hard to see what's going on, and impossible to edit by hand, because if you mess up with the metadata, that's it. So the good part, RDX, replicated data exchange format. So it is like JSON-like format, which has metadata on every piece of data in a proper way, but basically the model is built in a way that you may export it in a flat form and then import it back into metadata-rich form. So basically, as a user, you never work with metadata annotated data. Also, it is not exactly JSON because it is sort of optimized to make it nice, clean algebraic. So, for example, there are like primitive types, first float, integer, reference, string, term. And there are plex types, collections basically, tuple, linear, vector, Eulerian set, and multiplex is like a version vector or a counter, collaborative counter. So the idea is that you can nest it all arbitrarily. For example, this is a set. In a JavaScript, that will be illegal to have, for example, one entry or entry without a key, and here set is a set. So basically, you can put whatever you want into it, and this key value pair is actually a tuple, and this pair is also a tuple. So basically, it is like algebraically optimized JSON, where everything commutes and everything can be nested into everything. So basically, no matter how you merge it, you don't produce some illegal construction. Oh, the good part about this format, RDX replicated data exchange format, is that its merge operators are very much like merge sort operators. So it is like a parallel path of data, right? So it is a very common primitive in LSM databases, and basically you can take any LSM databases. RocksDB, my students did, and I personally did PebbleDB. You just take some LSM database, install a merge operator which basically does RDX merge, and suddenly you have an RDX database which can be merged like replica to replica, patches applied and everything. So this is my prototype implementation in Go. Students tortured RocksDB. It is prototype quality, but the idea is once you have all these constructs nice, clean, algebraic, you can just add these merge operators to a regular database, and it becomes mergeable, syncable CRDT database. This is a very primitive hack, and pam, it works. Because, once again, all the merge operator for all these types, they're like single pass, very much like merge sort. And then there is this library, which I write in very peculiar dialect of C, which is called ABC, algebraic bricklaying C. It is a very algebraic dialect. People who read it, they always mention Lisp and everything. And the good part, it is like systems level stuff. So librdx is like system. So the vision about this library is just have in every Linux like libgpeg, librdx. Just to sync data from any app to by any connection to any server. That is the idea. Mathematically all nice, but big code bases in C are a challenge, obviously, and in any other language. So, in this world of data syncing technologies, we now have a different problem. We have different standards for those data syncing outlets, very much like in the real world, but otherwise life is beautiful. And please, questions.
Thank you.
You have a first question, right? No. Okay.
Any question? Yeah.
Yeah, I have a question. So, would you consider Git as something that does sync and that you can use? And you didn't.
No, theoretically, I must put my stuff in text files and try syncing it with Git.
Sorry.
Some people are actually doing that. For example,
Can you repeat the question, please?
Huh?
Can you repeat the question?
Why don't I use Git? Why do I even consider?
Yeah, why didn't you list it as one of the things?
Why I list it? Because some people are actually doing it. For example, they put issues and comments and stuff into their repo with the main project, and they have some scripts, which like, I forgot how the name of the project which is doing that, but they're actually using Git to sync data. That is not correct, but it works to some degree. And rsync is the same. So basically, I'm just going like less semantics, more semantics. Rsync is just blobs. Git is basically also blobs, but it tracks history of the blobs and it can merge changes to the blobs without understanding semantics. And CRDT, everything of that, and also it has particular semantics for data structure. So it can merge set as a set and vector as a vector. So like primitive to sophisticated.
You brought up the merge problem earlier, but I don't know if I missed any proposed solution on semantic merge conflicts. So even with RDX or whatnot, what's your proposal for, I changed the word to cat, you changed the word to dog, and they come in together?
Obviously LLM. I mean, it was like a joke for like 20 years in this domain. Like we need artificial intelligence to solve semantic merge problems because they're semantic. And now we have artificial intelligence, so it is no longer a joke.
Just to clarify, leave it up to the application to choose.
Basically, they will produce a mess, but they will produce a deterministic mess. So they will all produce the same mess. So the one who resolves that mess will also resolve it for the others. At this algorithmical level, that is like the maximum possible thing.
Do you have a solution, or is it at a level above for compaction or garbage collection of the version vectors?
Yes. Basically, LSM databases, they do garbage collection naturally. Like the way they work, they always do GC. Like with every compaction, they basically compact. So more or less the same thing. Some amount of metadata still stays. It is inevitable, unfortunately. But in the general scheme of things, yes, there are compaction runs like in every LSM database.
Thank you.
Oh, finally.
So how do you actually like handle? Is it ends up being last write rins for like actual pieces of data, like on let's say between if it was name Alice Bob. Like there's a conflict in the actual values?
There is conflict. Basically, in many cases it is last retrieve. It depends on the data structure. In case of an array, for example, we somehow uniquely identify the insertion place. So if somebody inserts data into that place, we don't care about any concurrent insertions or deletions. We can always find the place in the new version. That is semantics of array. Sets, they have more or less last retrieve semantics, but very particular key. Counters have a different semantics. Like in one version we had like Bob 5, in the other version we have Bob 7. We know like this one is later version, so Bob 7. That means like Bob contributed 7 units to this particular counter.
Yeah.
And values from Alice, they will go like in a different cell. So basically concurrent counters, they split it by contributions by the source. Not to mess up the things, because they track who contributed how much. And so on. The semantics differs by the data type. Yep.
Yeah, sorry, I have another question. Should I understand RDX as being a CRDT? So could I say when I choose,
Sure.
I choose between auto merge, YJS,
Yes,
types,
yes.
and then now this is
This span was exactly about that. Yes, this span. You
Okay.
see, Klepman is
sure.
working in Cambridge. Yeah.
Referencing to auto merge. So is there also something about RDX that makes it different or higher up the stack or larger than YJS, for instance? Is there something that RDX does?
YJS is more or less like a small business doing JavaScript data synchronization for collaborative online applications, which was my state of things in 2012, 2014. And now I'm doing systems level stuff. So YJS, yes, that is yet another solution. If you speak of auto merge, then basically they're trying to use unchained JSON. And I'm basically saying, like, there's no way to make JSON mergeable. Let's make a nicer JSON-like format, which is like sufficiently, how to say it, algebraic to merge it nicely. So more or less like this. So these are different solutions, but they more or less like overlap heavily, but by 80% maybe.
Thank you. One last question.
Is this like mathematically proved that this problem is solved?
Yeah, that is a boring part.
So
yes,
why do we still have?
Yes, sure.
Why do we still have things like merge conflicts?
Basically, it was published. It was chain of articles starting 2006, I believe, and the term CRDT was coined in 2011, and it was always mathematically proved. Each single one was mathematically proved. So for the last 15 years, the problem was practical applicability because of the metadata. And in theory, everything merges nicely. Everything's perfect, like unicorns and rainbows.